All right, so the strategy function, right? As I mentioned earlier, all these strategies are basically trying to solve one thing, right? I'm just trying to calculate what should be my next move, right? In our particular case, right? So presumably, we could say that all strategies would implement this one function. What is my next move? Where should I move my piece? Knowing all my model, right? Knowing that I'm player X or O, right? Knowing the current state of the application, where should I next move, right? And if in the tax example, what should be my next deduction, right? So based on my particular circumstances, find what's my next deduction that I can deduct, my children, my house, my whatever, my boat. I don't have my boat yet. And see what could I calculate and keep deducing from my liability. And so they're all going to implement this function, this strategy function, right? Or what should be my next deduction, my next move. So in tic-tac-toe, the function might be something like play move, calculate my next move, given my current state of affairs, right, where we are in the however we're laying out the model of the tic-tac-toe game, where the X's are and the O's are, which and if I'm using arrays or whatever, or lists to represent this, calculate what should be my next move. And so it would be something like a function called play move that takes in the model, the current player, and comes back to saying, okay, player X or player O should move into position 3, 2 or something, right? So that would be the result. Okay? And the different strategies will come back with a different combination of results depending on that strategy. Right? One of them will come back with the corner. One of them will come back with any random selection of available spots. Other ones will try to decide whether I'm going to block someone else or going to move into the winning spot. Right? So the question is, how is it that each one of these strategies chooses? How do they calculate? So we'll see that they all implement this interface, which we'll see in a minute. Where is it? Choose move. They're all gonna implement the tic-tac-toe strategy, which is an interface. Right? It'll be an interface that basically this is the interface, right? Tic-tac-toe strategy. So all strategies, right, they're all going to implement this one function: choose a move. Given the current model of affairs, right? Where are the X's? Where are the O's? Calculate for me. For this player that I'm passing you, where should they move, right? And they'll come back with a coordinate, X and Y, or row, column, where should they move. For the model, right? It's a simple model, right? We have the height and the width of the board, right? That we have a set of pieces that we can ask. Where is X? Where is O currently? Right? What's the next move? Being able to actually move and change a spot on the board to an X or an O. Whether somebody has won yet, right? We can calculate who the current winner is. So the model keeps track of all this, right? Irrespective of how that is implemented. That's not the point, right? However, we use arrays or whatnot. There's some implementation. That's not going to be the focus. We're not going to implement the model. Instead, we would like to be able to iterate over this, right, and determine what should be the next move, right? So we're not going to spend too much time on the model. Instead, we'd like to be able to say, well, based on that model, how is it that I choose my move? And different strategies will implement the same. We'll implement this strategy. Will give us different versions of this choose move. And this is where we're going to come back a little later. Say, well, why not make this maybe an abstract class? Yes, and the different strategies would inherit from this class, from this top level class, right? As opposed to the way we're going to implement them using delegation, right? We're going to instead create an instance of these classes and then try to combine them together, right? If we took the inheritance route, we would have an abstract class, like the strategy abstract class, and then the simpler ones would inherit from this base class, and then more sophisticated ones would just add an override parent, override their children, right? Implementing ever more interesting implementations. Yes, but that would create a single inheritance chain, right? Where the most sophisticated implementation of our strategy would only inherit from its parent. Yes, and that one would inherit from its parent, and so on and so forth. So the strategy, or the ever more increasing sophisticated strategies, would only inherit from in one single line of inheritance. What if you wanted to combine them in any other ways? There's no way to dynamically, move them around, okay, and combine them in any other way other than that one hard-coded inheritance chain. Make sense? Whereas the way we're going to go, which is delegation, yeah, we're gonna choose one particular strategy of saying, well, let's do this one first and then that one. How about that? But we could at runtime, depending on our logic, we could combine them in any other particular order. Make sense? All right. We know a particular strategy that we know it's the correct strategy is that we go from the less sophisticated ones to the more sophisticated one. Yes, right. But we could have done it any other way at runtime. Perhaps later on we'll see that we could automate this. Maybe do like a simple AI where we could set the level of complexity and say, well, I want to play an AI and I want to play an easy mode, right? So I give it, well, use the dumb strategy, right? If I want to make it harder, I can dynamically say, ooh, I want to play a harder AI, right? And so they can choose dynamically at runtime, choose the more sophisticated strategy. Yes, and all this could happen at runtime as opposed to inherit, which we could not do by inheritance. That makes sense, right? Yeah. So let's take a look at implementing at least the simplest of these strategies, right? So the simplest of strategies will look something as follows, right? We'll call it the any open square strategy, right? It's its own class, right? It's implementing this one function, right? And the function here it could be done randomly, or it could be the first spot that we find that is open. We'll take that one, whatever, right? You can implement it in any different ways, right? But it says any open square, so that means that I could just walk the array either linearly, right, or randomly. That's up to you which way you want to do it. In any case, any open square is good, right? I don't really care which one. So in that strategy here, we are just walking the array, looking for the first available spot that is not already taken by some token, right? So we're just iterating over the height and the width of the model. And we're getting to see is there any piece in 0, 0? Yes, it's already taken. Okay, well, let's go to 0, 1, 0, 2, and then horizontally, and then vertically until we find something that is empty, and we just simply return that coordinate, right? It says, okay, well, this is your next move. Yes.
A quick semi-related thing about the coordinates. Why do we do coordinates in row-column notation instead of column-row notation, which would be more like a traditional x, y? Because row-column is like y-x.
Yeah, it's more like we're considering like tabular data, right? That's when you start looking at databases, and usually you iterate vertically, right? And then you consider a record, and then as you look at a record, then you look at the different columns or the fields in that. It's just one way that we abstractly represent data in general, is that we think of it vertically and then horizontally. Also, in Western societies, we tend to read from left to right and from top to bottom. So it's more of a I guess if we're more from an Eastern culture, perhaps we would be iterating backwards from right to left as opposed to left to right. Yeah, it's very cultural. So the open square strategy. Right. So certainly we could agree that this implements that that really simple, not very sophisticated strategy, right? That I'll take just any open square. So let's we'll create ever more increasing strategies, but we're not gonna let's not really focus on how is it that we play tic-tac-toe. That's not the point. The point is that we're going to be able to create ever more increasing strategies, perhaps more sophisticated, right? And what I really like to point out is that we're going to be able to combine them, right? That's the whole point, right? Of that we're going to be able to identify one particular sequence of these strategies are most effective, and we're going to choose one particular sequence and say, all right, well, obviously the overall strategy is I want to win, and then I want to block, and then I want to do the corners and whatnot. So we know of a particular strategy that we can implement, and we can combine them and re-implement them in terms of the more or less sophisticated ones that you can combine. That's the point that we want to reach at, right? That we can combine this in composition, either dynamically or programmatically, like we're going to do here, and that's really what we're going to drive at. Not the particular implementation, obviously. That's not the point, right? We don't really care. That's tic-tac-toe. So we have this very first, very simple strategy, and we could have chosen randomness. We could have already we know of that most sophisticated strategy. We could have gone just that way, right, and implemented the winning strategy and just call it a day. Yes, try to win, block, yada yada, and so on and so forth. But obviously that would break the whole lecture of breaking it up into smaller ones that you can then combine. That's the whole point that we want to show you. So let's implement the second strategy. And obviously the second one, we know that somehow it includes this first one. Yes, right. The second one kind of says, well, I want to play in the corners if I can, right? And if I don't have the corners, then I'll take any open spot. Yes, right. It looks like one includes the other, but that's not the point, right? We're not going to implement the whole logic in this one strategy. Instead, we're going to only focus on the corner strategy, and we'll see that we can leave the other half of that sentence, right, so that we can build it in terms of this one strategy that we just built, right? So here's the any open corner strategy. Right? Notice that the any open corner strategy doesn't really care whether all the other spots are available. It only focuses on these corners. That's all it really cares, right? It's not implementing the fallback strategy of saying, well, if there's no open corners, then I'll take any open spot, right? That will do next, right? To point out the fact that you can combine these two, right? For this to work, notice that this first strategy. Notice what this first strategy is doing, right? It's looking for the open spots, and when it doesn't find it, it returns null. See that? Right, so that flag of us returning null is what's going to let us know that, hey, that strategy didn't work. Right? And if all strategies follow that same strategy, strategies follow very meta. If all these strategies do the same thing, that if they fail, they just return null, right? That's going to allow us to combine these, right? As a means for us to tell, oh, this strategy failed, fall back into a dumber strategy, right? Okay, so yeah, so remember that return null. Yes?
So that would be that really the place where you would change and write return and then another lower level strategy basically?
Exactly. But that's what's going to allow us to combine them without any one of them knowing about each other. Right? That's the point, right? They don't know about the strategies, don't know anything about each other, right? It'll be a higher strategy that knows about the two and how to combine them into two.
You actually just return null.
Yeah, we just return null.
Okay.
Yeah. And a higher strategy, higher level strategy, we'll look at both of them and say, okay, well, let me use the smarter one, and if that doesn't work, then I'll use the dumber one.
Returns null then. So
Yeah, yeah. So we'll build a combining strategy that will take any two strategies, right? Any two particular strategies. We'll try them in sequence, and what that will allow us to do is to create a chain, a dynamic chain of strategies, right? Where we can take any two strategies together, and then the output of that can be combined with a third strategy, and the output of that can combine with a third or fourth and fifth and sixth strategy in general. Create any chain that we want, right, in any sequence, and we can do that dynamically at runtime. Yes? Okay. Yeah, so they all return null, and that will be our flag of knowing that this strategy failed. Right? We didn't find any open spot. Right? And since this is the dumbest strategy, probably that means that we lost, right, or we tied. Right? It means that we didn't find any open spots, and we either lost or we tied. Yeah? The board is full. Right, and it's time to determine whether somebody won or the game is tied. So let's take a look at the second strategy. So again, this second strategy, we could have written in here the second spot of saying, well, if this doesn't work, if the corners aren't available, then give me any spot, right? But that we already know that we already implemented that. We're going to leave that alone. So instead, the choose move only focuses on the corner. So 0, 0, 0, 2, 2, 0, or 2, 2. Right? It's going to look at these four corners. Are they available? Right? If they are, take them. Okay. So we return. Right? If there's no one at 0, 0, then take 0, 0. Right? If no one at 0, 2, then take 0, 2. Right? Very simple. And that's also the point, right? That each one of these strategies are self-contained. Okay. They have no dependencies on any other strategy, right? They can be used independently of everyone else, right? So we call that cohesiveness, right? It's self-contained. It does what it needs to do very well, and that's the only thing that it knows how to do. Okay. We have 2-0 and 2-2. Otherwise, if there are no corners, I failed. I'll come back with a null. Yes. All right. So having these two strategies, we could keep going. Third and fourth strategy, and so on and so forth, right? But before we consider the smarter strategies, right? Let's see how we would combine them. How could we combine them into ever more sophisticated strategies? And we'll do it in a way that they're generic, right? They're generic. You can pass any two strategies, yes, and you can validate which one would you choose. And if none of them works, then it will return null, right? So that you can combine it with an even more complex strategy, and so on and so forth. So let's see how we combine them.